Earth is a planet of living things. Virtually everywhere on Earth, you can find some form of life. Life in the sea. Life in the air. Life on land. What is it that makes Earth capable of sustaining life? Was Earth habitable before life evolved here? Or was it the other way around? Does life play a significant role in making Earth habitable today? The Earth's surface is made up of differing environments. The scorched deserts of Egypt, rain-soaked forests of Brazil, snow-covered forests of Canada, and the steaming jungles of Indonesia. How does life in one ecosystem relate to life in another? Are the rainforests of one continent in some way dependent upon the deserts of another continent? Are land and ocean independent, or does change in one affect the other? If humans change or destroy one ecosystem, do we threaten other delicate balances arrived at through eons of evolution? Scientists around the world are concerned that humans are causing possibly dangerous changes in Earth systems. They know that some forms of life are at risk. Humankind itself may suffer severely. Evidence of this global change is seen in many parts of the world. Among them is North Africa. The Sahara, like other deserts around the world, is expanding. The sands are always on the move, flowing before the wind. Blown by the relentless wind, the sands of the Sahara can smother what humans build. The moving dunes cut off roadways and slowly bury towns. This is a silent invasion that marches right down the streets of cities. Agricultural land is being covered as well. At the edges of the Sahara, people are displaced by the shifting desert. In the Sahel region, people are nomadic, moving with the changing land. As these hunters and gatherers use up the resources of one place, they pack up and go to another. The fragile landscape is harmed as they use its trees for firewood and their animals graze away its grasses. By destroying these grasses and trees at the edge of the desert, the Wahdabi speed up the natural expansion of the desert. The great ancient forests of the earth are also being changed by human activities. Once, forests covered nearly half of the Earth's land area, but today they cover only about 30%. Humans are largely responsible for this rapid decline. Some people want the forest for its timber. Other people clear the forest so they can homestead on the land. As demand for land and forest products increases, habitat is lost. The forests and the plants and animals in the forests are being lost at a time when we have scarcely begun to understand their roles on this living earth. The glaciers of the world are also undergoing dramatic change. The earth has gone through long periods of alternate warming and cooling. During cooling, the great glaciers grew in size. Today, many glaciers are melting. The toe of the Athabasca Glacier in the Canadian Rockies has melted back 1 kilometer in the last 60 years. Could this be evidence of global warming? And if it is, are human activities speeding up the worldwide melting of glaciers? Faced with a rapidly changing Earth, scientists are struggling to understand how all parts of the Earth, the living and the non-living, work together as a system. The history of our planet's development provides some clues. About 4 billion years ago, the interior of the young Earth was much hotter, its surface volcanic. At that time, the sun was weak. About 1/3 less solar energy reached the Earth than does today, and the surface should have been colder. But volcanic vents spewed gases into the air, creating the new atmosphere, which covered the Earth like a giant blanket. Among the volcanic gases were carbon dioxide and water vapor. Just as a greenhouse lets in sunlight and traps the heat, these so-called greenhouse gases blanketed the Earth and warmed it. But the sun grew steadily warmer, and had the greenhouse effect continued, the Earth would have become too hot for life. Why didn't this happen? Some scientists think that life itself is the answer. Early forms of life were present as much as 3.5 billion years ago. Some of the earliest living things were algae, which extracted carbon dioxide from the air and built large mounds of carbonate called stromatolites. By changing the gas mixture of the atmosphere, the algae moderated the climate, preventing overheating. Life still actively withdraws carbon dioxide from the atmosphere. For example, the massive coral reefs found throughout the tropical oceans are essentially made of carbonate. Algae and marine animals, including corals, build reefs by extracting carbon dioxide from the air. Carbon dioxide is also a major building block of today's forests. During photosynthesis, plants take in carbon dioxide and water, convert them to sugar, and expel oxygen. Although this process is commonplace, on land as well as in the ocean, it is difficult to observe unless the plants are underwater. When a seagrass photosynthesizes, tiny oxygen bubbles can sometimes be seen forming around its leaves. Living things naturally modify the composition of the atmosphere and therefore affect the climate of the Earth. But today, there are new complications brought on by human activities. These changes are being measured at the top of Mauna Loa volcano on the island of Hawaii. 3,400 meters above the ocean, a research station is operated by the National Oceanic and Atmospheric Administration. Since the 1960s, it has continuously monitored the composition of the atmosphere. John Chin regularly comes up the mountain to maintain the equipment and make measurements. The station is ideally located, thousands of kilometers from the nearest continent and thousands of meters up in clean air. So there are few contaminants to affect the measurements. Over the years, the measurements have revealed a natural seasonal pattern. In winter, plant activity slows, causing the carbon dioxide content of the air to rise. In summer, plant activity increases, causing the carbon dioxide content of the air to fall. These annual cycles are normal, but in recent decades, the overall trend worldwide has been up. This buildup of carbon dioxide in the atmosphere has many scientists worried. To gain some perspective of the rapid increase in atmospheric carbon dioxide, some scientists are looking back over time at the content of Earth's atmosphere many thousands of years ago. One of the best places to do that is on the continent of Antarctica. In the vast expanses near the South Pole, frozen in ice, is the very same air that surrounded Earth tens of thousands of years ago. By analyzing ice cores, scientists are able to determine the composition of the ancient atmosphere. In a huge freezer at the State University of New York at Buffalo, researchers store and examine ice cores. Scientists have discovered that the Earth's climate has swung between ice ages, when the carbon dioxide levels were low, and warmer periods like today, when those levels are high. Researchers who study these ice cores think that the Earth has warmed about 2 to 3 degrees Celsius in the last 18,000 years. Other scientists project that in the next 100 years, the Earth may warm another 2 to 3 degrees Celsius. Such a rapid change has not occurred in human history and is of real concern.
Oh, it is. This is approximately a meter and a half.
How does life respond to such drastic changes in the composition of the atmosphere? Christine Ennis at the National Center for Atmospheric Research finds that plants respond significantly to atmospheric changes. The ability of some plants to photosynthesize is reduced in the presence of certain compounds, such as sulfur dioxide and ozone. Both of these compounds are produced by human activity and dumped into the atmosphere. The early evidence is clear. Human actions are changing the atmosphere, and these changes are affecting life. In an urgent effort to understand the dimensions of global change, scientists are building new and better space-based platforms from which to view the changing Earth.
Transfer to inch, about 1.5 feet. 1.5 feet.
New satellites, such as this one at Ford Aerospace in California, provide enormous amounts of data.
Okay. Uh-oh, screaming bolts. Okay. A little pressure in the rear, slowly.
This information from space provides minute detail, documents change over time, and enables scientists to see with new eyes. New methods are needed to collect, store, and manipulate the vast amounts of data provided by the satellites. At laboratories like the National Center for Atmospheric Research in Boulder, Colorado, scientists use powerful new supercomputers to manage the information. For example, we can see more clearly the global distribution of solar energy, which strongly governs the abundance and distribution of life. More solar energy is received at Earth's midsection than near the poles. This concentration of heat near the equator is distributed both north and south by winds. Atmospheric storms are one way heat is distributed over the Earth. In addition, heat near the equatorial region is absorbed by the ocean and then distributed by currents moving toward the poles. The Gulf Stream is such a current. It brings warm Caribbean waters to Great Britain, moderating that country's climate. Using such knowledge, scientists can build models to help explain how the Earth system works. Tom Betke of the National Center has assembled a model projecting the consequences of an increased quantity of atmospheric carbon dioxide. If carbon dioxide doubles in the next 100 years, which many scientists think quite possible, the global temperature will rise. The model indicates, in red, the areas that will be most affected. Another critical component of the Earth system is the moisture cycle. This cycle is driven by solar heating, which makes the equatorial region warmer than the rest of the Earth. Warm, moist equatorial air rises and cools. The water vapor condenses, clouds form, and rain falls. Around 30 degrees north and south of the equator, the dry air slowly descends. The broad patterns of rainfall on Earth are closely related to this cycle of winds and temperature. At the equator, we find the zones of heaviest rainfall, and within them, the tropical rainforests of the Americas, Africa, and Asia. At 30 degrees north and south latitude, we find the vast dry zones and the deserts of North and South America, Africa, Asia, and Australia. The Amazon rainforest of Brazil in South America is dependent upon these patterns. The Amazon rainforest is located within the equatorial rainfall belt. Easterly winds carry moisture from the ocean over land. These clouds drop much of their moisture on the forest below. The plants and soils of the forest act like a sponge, absorbing the rainfall and then, under heat, releasing this moisture through evaporation and transpiration back to the sky. This moisture from the forest can fall again as rain in a continuing cycle. The cycle begins anew when dawn comes to the Amazon, bringing heat. Much of the previous afternoon's moisture begins to rise. Fog left by the cool night blankets the forest. As the forest warms, the moisture rises and eventually becomes part of the afternoon storm clouds. By mid-afternoon, the cycle begins to repeat itself. With the aid of satellite sensors, scientists from the University of Wisconsin and the Federal University of Para in Brazil are studying the water cycle of the Amazon rainforest.
From the ground, you could never, ever have any idea how much rain or how these systems organize themselves. We just know, oh, it's gonna rain. Oh, it stopped raining. And then we just see one cell at the time.
Ellen Coutream and Dave Martin use satellite imagery to gain an overview of the forest's moisture cycle.
Make deflect, but upwards, the
Enhance precipitation without
enhance,
slope.
yes.
The wind's blowing up the Andes.
The infrared or heat-sensing satellite sensors help the scientists map and measure rainfall patterns.
It's amazing how fast it changes.
Coutream and her colleagues are trying to understand how the forest helps to maintain the water cycle and the climate of the Amazon region. But they are also concerned about larger issues. The evaporation of moisture from the tropical rainforests requires heat. This heat enters the atmosphere along with the moisture and is distributed around the globe. But if the rainforests continue to be destroyed, the moisture cycle may break down and the global heat system will change. The tropical regions will likely become hotter and drier. Scientists are also concerned about what will happen to climates elsewhere in the world as the forests are eliminated. Many people believe that the ocean may act as a flywheel, moderating the effects of global change, producing oxygen, consuming carbon dioxide, and absorbing heat. The ocean is undoubtedly of critical importance, but our understanding of it is limited. People in different fields are trying to understand the complex processes and forces that drive this restless environment. Chris Harold, a marine biologist, is studying plant life and its role in ocean systems. Most oceanographic research, like Harold's study of kelp forests in Monterey Bay, deal with relatively small areas. After all, the ocean is vast and complex. Increasingly, though, scientists seek to understand the global role of the ocean. Interestingly, some of the answers are hidden in some of the tiniest and most widespread life forms on Earth, the microscopic plants called phytoplankton. Tim Coles of Oregon State University studies these organisms in the microscopic dimensions of their world. High magnification reveals their intricate structures. Coles has been studying phytoplankton's absorption of light and their concentration at different depths in the ocean. How and where phytoplankton live is important to understand because as they grow, they do something astonishing. Phytoplankton help to form clouds in the atmosphere. One group of scientists has been studying this process by making measurements simultaneously in the ocean, in the air directly above the ocean, in the atmosphere very high above the ocean, and in this same air as it drifts in from the sea over the state of Washington. The scientists know that phytoplankton produce a certain sulfur compound that passes into the atmosphere. The special property of this compound is that it provides a surface around which water droplets and then marine clouds can form. To study this link between sea and air requires close coordination.
Noah Ship MacArthur. This is Chica Peak calling Noah Ship MacArthur Fantail, over.
Go ahead, Chica Peak.
Hi, Tim. Just like to exchange some data with you here for the noontime report. Our DMS...
These scientists with the Pacific Sulfur Stratus investigation are tracking the upward development of this type of marine cloud. The tracking begins at sea with the collection of water samples containing phytoplankton.
The winds never come up, we'll just keep doing 48 hours.
The tracking continues at the laboratory on land, where another scientist collects, then records the tiny cloud droplets on a video screen. The scientists think that cloud formation by phytoplankton is important because these marine clouds reflect sunlight back into space, preventing some heat from reaching the Earth. So the phytoplankton, acting on a global scale, might cool the Earth. Whether such a cooling might help offset a global warming caused by human activities is not yet known. As we improve our abilities to envision the Earth as a whole system, in all its rich complexity, we approach the threshold of a new understanding of our living Earth. The processes of global life are intimately related to those of the air, the land, and the sea. Life depends on these physical systems, but in turn participates vigorously in governing them. The continued health of the global environment as a habitat for humans, for all life, depends critically on our future behavior. To guide our activities intelligently, we must continue to expand our vision of the living Earth in all its glorious detail and of our place in it.